Okay, so for the example of cylindrical uh, conduction, we have a given here an insulated pipe, a given ambient temperature, inside diameter, with a wall. This is initially probably or the pipe. This is the pipe. The outside diameter of the corrugated asbestos is insulation is 135. The surface coefficient of steel area is okay. And inside the pipe, having an inside temperature or steam having a 100 Celsius with field coefficient of 6,000 watt per square meter K. Thermal conductivity pipe and asbestos solution are 45 and 0.12 watt per meter Kelvin. Determine the heat loss per unit length of pipe. So we have a multiple layer, no? So we can imagine this first. No? So you have a pipe, find the pipe, that pipe first. No? So the pipe has a radius, sorry, a diameter, no, of 50 meter or millimeter. So the radius is 25 millimeter, no, millimeter, and then it has a 10 millimeter wall. No? This pipe has a 10 millimeter wall. So we have a 10 millimeter wall here. We have 10 millimeter. So therefore, the other radius here, you can imagine, is what? This is 35 millimeter. Okay. And then you have a corrugated asbestos insulation. So diameter of the corrugated asbestos. So this will be 125 all throughout, no? So this will be probably larger. So you have another layer here, which is this insulation. Um, so as you can see, you have this layer here. And the outside diameter now is 125. So we can divide this by 2. So this will be 62.5. 62.5 mm, right? Okay. And then you have a definition of the coefficient of steel air, the inside, and also the inside and outside temperatures. Okay, and then I think that's it. Thermal conductivity of the insulation and the pipe is also given. So to find for the Q of the cylinder, we just want to find the temperature difference. So T1 minus T2. So T hot minus T2 yan. And then you have R total. So to find R total, okay, so the R total here, let us define this one by one. So the first one is the inside. No? The inside here is 1 over HI times what? Ano ba yung area niya? No? So you have to define the area. So the area is consistent din naman dito. No? So 1 over HI, remember? HIA, and then 2 pi L tayo sa kabila. No? So plus, for the first layer is the pi. So you have 1, LN pala, no? LN, you have um, I'll just write here 35 over 25, no? Because this is the thickness of the pipe, no? So over 2 pi L, so 2 pi L and then A, uh, plus you have LN. So the ratio of the outside, so 62.5 over 35 over 2 pi L K. And then the last one is 1 over HOA. Oh, okay, that's it. You can find the third total resistance. So this will be 1 over HI 6,000. So we don't have an area pala, no, that we can factor out. So we have to solve for the area, which is 2 pi L, no? 2 pi LR, no? 2 pi RL. So 2 pi R, so the radius inside is 25 millimeters, so 0.02 0.25, and then times the length, which is it given? Okay, it is not given, so per 1 meter unit length na lang, no? So we'll just assume 1 meter unit length of the pipe per 1 unit. Okay, and then plus ln of 35 over 35, and then we have 2 pi L, L. L here is what? No? L here is still L, no? So we have 1 meter only. And then K is given as for the pipe. So 45 watt per meter Kelvin, no? So it's like a second one. And then plus you have ln 62.5 over 35. And then you have 2 pi lk. So 1 and then k is 0.12. No. And then 1 over ho. So we have 12. And then you have 2 pi L, no? So 2 pi RL. So R here is 62.5. And then the length is 1 meter only. So we have to convert this pala, ano? Forgot to convert this. 0.0625. Okay. So unit analysis, we have here watt per meter squared Kelvin. So this is meter squared. So you have watt per Kelvin. And then, I'm sorry, it will be Kelvin per watt. This will be unitless. This is meter. Okay, not really. Yes, meter. And then this is watt per meter Kelvin. So Kelvin per watt again. So I think those for this one. So the R total is equal to, so yeah, let's use the calculator at this point. 1 over 6,000 times 2 pi times 1.025 plus ln log over 25 times 45 n. Okay, plus ln 62.5 over 25. Then you have 2 pi times 1 times 0.2. And then plus you have 1 over 12 times 2 pi times 0.065. So yeah, 0.98. No? 0.98. Sorry, it's down 25 Kelvin per watt. No? So solving for this, so we have a temperature difference of 32 and 150. So 150 minus 32 over 0.9835. So the answer is 119.98. So to find the Q, have 150 minus 32, 8 divided by 0.9835. That will be about 120 watts. Okay, it's that simple. Okay, so we have another one here. So a 3 millimeter diameter and 5 millimeter long, meter long and 2-wire slightly wrapped with a 2 millimeter thick flex forward with this given thermal conductivity. The electrical measurements give 10 amperes voltage drop. If the insulated wire is exposed at 12 medium, if it is with a transfer coefficient of 12, determine the temperature at the interface of the wire and plastic over any steady creation. Also determine whether doubling the thickness of the plastic over will increase or decrease this interface temperature. Okay, so we want to find the temperature of the interface of the wire and the plastic cover in steady operation. So we have to first visualize, no, this setup. So we have a 3 millimeter diameter wire. So you have 3 millimeter diameter, or in other words, you have 1.5 millimeter diameter wire, radius wire, which is how long, no? So we have a length of 5 meter long, and then yeah, it is wrapped in a 2 millimeter thick. So we have a thickness here about 2 millimeters. I think it is too thick. Too thick. So you have here a 2 millimeter thick, 2 mm. No? So therefore, the radius here will be what? So 1.5 plus 2. So this will be 3.5. No? 3.5. So the K, the conductivity is given. Voltage drop in ampere or current is given. Outside the temperature, outside the wire is 30 degrees Celsius. We want to determine this temperature here, no? So this temperature here is what? This interface temperature. So just write T here for now. But how do we solve for this? So to find the Q of a cylinder, you have um, this is Ka, no? Ka T1 minus T2. In this case, you have T infinity as I think this is hotter, no? So we have T minus T infinity. Just use surface. So if you have conduction pala, no? Conduction and convection pa pala. Sorry. So this should be total resistance, no? So we should use the old classic T T1 minus T2 over R total. So the R total here is conduction and convection pala, no? So for the conduction, you have Ln of 3.5 over 1.5. Also the ratio of the outer and the inner diameter. Diameter, the radius, sorry, but diameter will also work actually. And then you have 2 pi KL, no? So 2 pi KL. Sorry. Sorry, I always forget the formula of the 2 pi LP. L is 5 meter long, so 5. And then the K here is 0.15. Okay, so this is for the conduction part. So for the convection part, you have 1 over HO area, right? So HO here is 12, no? 12 watts per meter Kelvin. Okay, here's where Kelvin. And then the area here is 2 pi. Also the surface area, 2 pi RL. Also R here is the outside radius. Usually we have to consider changing the units here to meters. So we have 0.0035. And then the length, not 2 pi RL, so 5 meters. I think that's it. Okay, so to find R, so the R total here. So as you notice, I didn't change the unit of 3.5 and 1.5. You can convert that to meters, but since they will cancel out, I didn't change the units of 3.5 and 1.5 for the Ln portion of the formula. 2 pi 5 times ah, it's 2.5. 12 times 2 pi is 0.00. So we have 9.9377, no? So the 0.9377. So the unit should be Kelvin per watt. So now we have this given. The T2 is given. This is actually your T infinity. We don't know the T1 because this is the T1, no? We don't know actually the Q, but we are assuming that the Q here is also the heat loss, no? Heat loss during yung PA is equal to IV natin. No? So what we can do here is to equate your Q. No? So PIV is equal to Q So Q is equal to PIB, or equal to P is equal to IB, which is, yeah, which is in amperes. So you have 10, and then you have 8. So this is in watts. And then you have T1 minus T infinity. T infinity is 30 all over 0.9377. So T1 here can be solved. To solve this mentally, So 10 times 8 times 0.93, 77 plus 30. So the answer is 105.16. 105.016 watts. No? Okay, so that's it for the interface temperature, of this copper wire, or whatever wire is this. Now the other question here is determine whether doubling the thickness of the plastic cover will increase or decrease the interface temperature. So the concept of critical radius of insulation is that if the radius of insulation, sorry, yes, the radius of insulation is less than the critical radius, then it will increase the heat transfer rate. But if it is above the critical radius, then it will decrease. No? So we want to determine the radius of critical, the critical radius of insulation. This is just K over H, for cylinders. So this is 0.15 watt per meter Kelvin. You can write that down. And then you have 12 watts per square meter Kelvin. So the critical radius here is uh, 0.15 over 12. So this is in meter, no? But if you convert this into millimeter, we can just multiply 1,000. You have 12.5 millimeter. No? So what does that mean? The radius that we have for the insulation is 3.5. No? So the radius of the insulation is 3.5, which is less than 12.5, which means, no, if it is less than the radius of insulation, then the heat transfer will increase. So yung Q nyo is increasing pa rin. Okay? I mean, if you double the thickness, no, let's say this will become 7, no? So if you double the thickness, sorry, I think this is the double insulation nga pala, no? If you multiply this by 2, this will become 7, which is still within the 12.5, then this will increase. But vice versa, if this is greater than, then this will be decrease. Okay, if it is equal, then it is at this peak, no? Wherein the conductive heat transfer is equal to the convective heat transfer. Okay, so that's it. Okay, so thank you guys, and see you.